In probability theory and statistics, kurtosis is any measure of the peakedness of the probability distribution of a real-valued random variable. In a similar way to the concept of skewness, kurtosis is a descriptor of the shape of a probability distribution and, just as for skewness, there are different ways of quantifying it for a theoretical distribution and corresponding ways of estimating it from a sample from a population. There are various interpretations of kurtosis, and of how particular measures should be interpreted. These are primarily peakedness, tail weight, and lack of shoulders. One common measure of kurtosis, originating with Karl Pearson, is based on a scaled version of the fourth moment of the data or population, but has been argued that this really measures heavy tails, and not peakedness. For this measure, higher kurtosis means more of the variance is the result of infrequent extreme deviations, as opposed to frequent modestly sized deviations. It is common practice to use an adjusted version of Pearson's kurtosis, the excess kurtosis, to provide a comparison of the shape of a given distribution to that of the normal distribution. Distributions with negative or positive excess kurtosis are called platykurtic distributions or leptokurtic distributions respectively. Alternative measures of kurtosis are, the L-kurtosis, which is a scaled version of the fourth L moment. Measures based on 4 population or sample quantiles. These correspond to the alternative measures of skewness that are not based on ordinary moments. Pearson moments, the fourth standardized moment is defined as where I1/4 is the fourth moment about the mean and I is the standard deviation. The fourth standardized moment is lower bounded by the squared skewness plus 1. Where I1/4 is the third moment about the mean. The fourth standardized moment is sometimes used as the definition of kurtosis in older works, but is not the definition used here. Kurtosis is more commonly defined as the fourth cumulant divided by the square of the second cumulant, which is equal to the fourth moment around the mean divided by the square of the variance of the probability distribution minus 3. Which is also known as excess kurtosis. The minus 3 at the end of this formula is often explained as a correction to make the kurtosis of the normal distribution equal to 0. Another reason can be seen by looking at the formula for the kurtosis of the sum of random variables. Suppose that y is the sum of n identically distributed independent random variables all with the same distribution as x. Then, this formula would be much more complicated if kurtosis were defined just as I1/4/AI4 florins. More generally, if x1, xn are independent random variables, not necessarily identically distributed, but all having the same variance, then whereas this identity would not hold if the definition did not include the subtraction of 3. The fourth standardized moment must be at least 1, so the excess kurtosis must be a 2 or more. This lower bound is realized by the Bernoulli distribution with p equals a 1/2, or coin toss. There is no upper limit to the excess kurtosis and it may be infinite. Interpretation: the exact interpretation of the Pearson measure of kurtosis is disputed. The classical interpretation, which applies only to symmetric and unimodal distributions, is that kurtosis measures both the peakedness of the distribution and the heaviness of its tail. Various statisticians have proposed other interpretations, such as lack of shoulders, or bimodality. Belander and McGillivray assert that the standard definition of kurtosis is a poor measure of the kurtosis, peakedness, or tail weight of a distribution, and instead propose to define kurtosis vaguely as the location and scale-free movement of probability mass from the shoulders of a distribution into its center and tails. Terminology and examples: a high kurtosis distribution has a sharper peak and fatter tails, while a low kurtosis distribution has a more rounded peak and thinner tails. Distributions with zero excess kurtosis are called mesokurtic, or mesokurtotic. The most prominent example of a mesokurtic distribution is the normal distribution family, regardless of the values of its parameters. A few other well-known distributions can be mesokurtic, depending on parameter values. For example, the binomial distribution is mesokurtic for. A distribution with positive excess kurtosis is called leptokurtic, or leptokurtotic. Lepto means slender. In terms of shape, A leptokurtic distribution has a more acute peak around the mean and fatter tails. Examples of leptokurtic distributions include the student's t-distribution, Rayleigh distribution, Laplace distribution, exponential distribution, Poisson distribution and the logistic distribution. Such distributions are sometimes termed super-Gaussian. A distribution with negative excess kurtosis is called platykurtic, or platykurtotic. Platy means broad. In terms of shape, a platykurtic distribution has a lower, wider peak around the mean and thinner tails. Examples of platykurtic distributions include the continuous or discrete uniform distributions, and the raised cosine distribution. The most platykurtic distribution of all is the Bernoulli distribution with p equals a 1/2, for which the excess kurtosis is a 2. Such distributions are sometimes termed sub-Gaussian. Graphical examples, the Pearson type 7 family. The effects of kurtosis are illustrated using a parametric family of distributions whose kurtosis can be adjusted while their lower-order moments and cumulants remain constant. Consider the Pearson type 7 family, which is a special case of the Pearson type 4 family restricted to symmetric densities. The probability density function is given by where A is a scale parameter and M is a shape parameter. All densities in this family are symmetric. The kth moment exists provided ma car plus A1/2. For the kurtosis to exist, we require ma A5/2. Then the mean and skewness exist and are both identically 0. Setting A2 equals A2 ma A3 makes the variance equal to unity. Then the only free parameter is M, which controls the fourth moment and hence the kurtosis. One can reparameterize with, where is the kurtosis as defined above. This yields a one-parameter leptokurtic family with 0 mean, unit variance, 0 skewness, and arbitrary positive kurtosis. The reparameterized density is in the limit as one obtains the density, which is shown as the red curve in the images on the right. In the other direction as one obtains the standard normal density as the limiting distribution, shown as the black curve. In the images on the right, the blue curve represents the density with kurtosis of 2. The top image shows that leptokurtic densities in this family have a higher peak than the mesokurtic normal density. The comparatively fatter tails of the leptokurtic densities are illustrated in the second image, which plots the natural logarithm of the Pearson type 7 densities. The black curve is the logarithm of the standard normal density, which is a parabola. One can see that the normal density allocates little probability mass to the regions far from the mean, compared with a blue curve of the leptokurtic Pearson type 7 density with kurtosis of 2. Between the blue curve and the black are other Pearson type 7 densities with I^2 equals A1, 1/2, 1/4, 1/8, and 1/16. The red curve again showed the upper limit of the Pearson type 7 family, with the red curve decreases the slowest as one moves outward from the origin. Kurtosis of well-known distributions. Several well-known, unimodal and symmetric distributions from different parametric families are compared here. Each has a mean and skewness of 0. The parameters have been chosen to result in a variance equal to 1 in each case. The images on the right show curves for the following 7 densities, on a linear scale and logarithmic scale, de Laplace distribution, also known as the double exponential distribution, red curve, excess kurtosis equals 3, s, hyperbolic secant distribution, orange curve, excess kurtosis equals 2, l, logistic distribution, green curve, excess kurtosis equals 1.2, n, normal distribution, black curve, excess kurtosis equals 0, c, raised cosine distribution, cyan curve, excess kurtosis equals a 0.593762. W, in a semicircle distribution, blue curve, excess kurtosis equals a 1, U, uniform distribution, magenta curve, excess kurtosis equals a 1.2. Note that in these cases the platykurtic densities have bounded support, whereas the densities with positive or zero excess kurtosis are supported on the whole real line. There exist platykurtic densities with infinite support, For example, exponential power distributions with sufficiently large shape parameter b, and there exist leptokurtic densities with finite support. For example, a distribution that is uniform between a 3 and a 0.3, between a 0.3 and 0.3, and between 0.3 and 3, with the same density in the end intervals, but with 20 times more density in the interval, sample kurtosis. For a sample of n values, the sample excess kurtosis is where M4 is the fourth sample moment about the mean, M2 is the second sample moment about the mean, Xi is the F value, and is the sample mean. The variance of the sample kurtosis of a sample of size n from the normal distribution is. An approximate alternative is 24/n, but this is inaccurate for small samples. Estimators of population kurtosis. Given a subset of samples from a population, the sample excess kurtosis above is a biased estimator of the population excess kurtosis. The usual estimator of the population excess kurtosis defined as follows. Where K4 is the unique symmetric unbiased estimator of the fourth cumulant, K2 is the unbiased estimate of the second cumulant, M4 is the fourth sample moment about the mean, M2 is the second sample moment about the mean, Xi is the F value, and is the sample mean. Unfortunately, is itself generally biased. For the normal distribution it is unbiased. Applications. D'Agostino's K-squared test is a goodness of fit normality test based on a combination of the sample skewness and sample kurtosis, as is the Jarkey-Beira test for normality. For non-normal samples, the variance of the variance depends on the kurtosis. For details, please see variance. Pearson's definition of kurtosis is used as an indicator of intermittency and turbulence. Other measures of kurtosis. A different measure of kurtosis, that is of the peakedness of a distribution, is provided by using L moments instead of the ordinary moments. See also, kurtosis risk, references. Further reading, Kim, Taiwan and White, Halbert on more robust estimation of skewness and kurtosis, simulation and application to the S&P 500 index. Finance Research Letters, 1, 56 €70 doi, 10.1016 per second 1544-6123, 03, 00003-5 Alternative source, Syria, E. and Bonnet, D.G. Two families of kurtosis measures. Metrica, 58, 59 €70. External links, Haswinkel, Michiel, ed., Excess Coefficient, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Free online software computes various types of skewness and kurtosis statistics for any data set. Kurtosis on the earliest known uses of some of the words of mathematics, celebrating 100 years of kurtosis, a history of the topic, with different measures of kurtosis.